FA divided by F, that is equal, let's say, to 2. So this is very positive. But we'll have a TSFC A divided by the TSFC that is more equal to 3, which is a very negative case. But in everything you have advantages and disadvantages. Huh? That means you will burn an enormous quantity of fuel. So you will be in afterburning during very short periods. You are burning 6-7 times more fuel than without afterburning. But you have a huge FA. And also, due to this, you have a huge thrust. And so, you can build a larger aircraft. In order to take more fuel and be able to fly supersonically, even if you have a very large fuel flow. So this aircraft will be a priori a big aircraft, because you need a lot of fuel, but you have a lot of thrust, so you will build this aircraft big. If you go to the bypass ratio here, you will not have a very good afterburning TSFC, non-afterburning TSFC. It will not be a good one. This is negative. This was positive. So you will have FA divided by F that is more 1.5. Okay, this is rather good. But you will have the TSFC A divided by the TSFC that will be around 2. So this is negative, but less negative than there. And so you could imagine, okay, but then what is the advantage of this case compared to this case? This is dF divided by m dot. F divided by m dot. Here, in this case, without afterburning or with afterburning, you have a lower bypass ratio. Remember, we have always set m dot P is equal to m dot turbojet. Never forget this assumption. Our rationale is based on that. And if you have a low bypass ratio, you have FA and F divided by m dot, that will be larger than here. So what do you see in our two families that we have developed? We have here an engine that is able to have a huge increase of the thrust, but at the expenses of a very high fuel burn. And here we have created an engine that is oriented to something else, increasing the acceleration capability. Okay, this is an observation. Of course, when you observe that, you can think about what about the other parameters? I remind you our equation that we have sometimes put here on this board. I have said that the thrust and the TSFC are depending on working parameters, PA, TA, Mach number, and the PLA that you can take as the rotational speed, for example, but also it's depending on the design parameters. And originally, I remind you that the design parameters, we had only 2, okay? When you switch to the turbofan, we have called that P global, we have added the P low pressure compressor, and we have also added the bypass ratio. And when you add the afterburning, you are adding, in fact, a fifth parameter. And so, in fact, the turbofan with afterburning is the most complicated engine that we have studied, with 5 design parameters. And so the question is, certainly, what are you doing in this case and in this case with this and with this? Knowing that this is fixed by the bypass ratio somewhere, this is depending on the bypass ratio. We have discussed the bypass ratio, we have discussed this one we know is higher and higher and higher, but what are the values that you take for these two ones? And what will you do? Of course, you will choose this one and this one, in this case, to play with the TSFC, and here to play with the specific thrust. So, how will you select P global in this case? If you want to increase the specific thrust, P global is small, and if you want to increase the selection of PLPC is what? You need to have a high VJS. You need to have a high ejection speed for the specific thrust. So, how will you select the PLPC? Large. That's why I've called that LPC and not fan, because you want to have a high LPC. Here, the low pressure compressor will not be a one stage. It will be a 2-stage, a 3-stage, a 4-stage, maybe. Okay? And in the other case, here, or are you selecting P global or are you selecting PLPC? P global, you will select large, because we want to reduce the TSFC, and the PLPC, you will select it small. And so, for example, here you will have only 2 stages, maybe 3 stages, and here you can have 3 or 4 stages in the low pressure compressor. And this is changing a lot, because you see, we have a small P global and a large PLPC. So that means that you have a big LPC and a, let's say, small HPC. Whereas in the other case here, you have, I'm exaggerating a bit, a small LPC, and here you will have a large HPC. Because P global is large, and this one is small, so you need a very large high pressure compressor, and here a much smaller. You see, it's the same engine. Mixed turbofan with afterburning. Here, very low bypass ratio, a big LPC, a small HPC. Here, a very large bypass ratio, let's say a large bypass ratio, a small LPC, a large HPC. Totally different engines for 2 different missions. Which missions? This mission is what we call a fighter. This aircraft, this engine is for an aircraft that you call a fighter, because it's oriented towards increase of the specific thrust, acceleration capability. Here, this is what we call a bomber, or also a reconnaissance aircraft, because it's flying very often subsonic, and at a certain moment it's flying supersonic in order to avoid the radars or things like that, in order to avoid the enemy or to increase the altitude at a certain moment. And he will be flying very often supersonic. And then he will switch to supersonic, or increase its thrust by the afterburning, even if it stays subsonic, but he will be able to do it thanks to what we have explained here. Of course, if you cannot choose at the beginning, you say you cannot choose at the beginning, you will select something here in between. So you will make an aircraft that is not this one, that is not this one, that is not as good as this one in this mission, not as good as this one in the other mission, and this is what we will call a fighter-bomber, mixture of the two, and you will take maybe a bypass ratio of 0.7. Here, so the P global, it depends on the TIT, of course. Here, maybe you take 32. Here, maybe you take only 24. Here, you will take 28. For the PLPC, here, maybe you take 4, even 4.5, maybe. Here, you will take only 3. And so you see 32 divided by 3, the PHPC, it's about 11. Here, 24 divided by 4.5, this is only 5. You see, the PHPC is 2 times smaller. And then you will choose, of course, something in between. Here you will choose for the PLPC 3.5, for example. And you will have for the HPC 20A divided by 3.5, and this is very easy, this is 6. No, this is 8. This is 8. You see, between 11 and 5, 8. Very different. And that's why. So after you will have followed this class, if you are again listening to people speaking about selecting an aircraft for military application in a country, and that people are comparing apples and pears, I think that you can look again at this board. If you have an aircraft that has an engine that has been done to do this mission, this engine will never be able to do this mission and will never be able to do this mission. If you buy a bicycle, you will never be able to go on a Formula 1 Grand Prix with your bicycle. So, if you are once in your life a decider, a minister, a politician, so please don't say things that are not the truth to the citizens. So, if you buy an engine that is this one, for an aircraft that is this one, this aircraft will never be able to do this, even if this aircraft is costing 4 billions. So look at this table once in your life if you are taking decisions, and I hope that you will not, like some people, say something else than the truth, okay? Even, of course, if the people are not understanding what you are saying at that moment, okay? So, very interesting. Very interesting because we have, in fact, discussed here the most complex engine of all engines that we have discussed.